When you hear the name Alan Turing, what comes to mind? Probably a wartime codebreaker or maybe the father of computer science. And sure, he was both of those things, but his real legacy, it's something so much deeper. He didn't just invent machines, he gave us a completely new language to ask some of the biggest questions imaginable. Questions like, what does it actually mean to compute? What is intelligence, really? And maybe the most profound of all, are there some things we just can't ever know?
So here's how we're going to break that down. We'll start with the one question that really kicked off a revolution. Then we'll dig into how Turing defined what it means to think mechanically and where its limits are. From there, we'll see how he totally redefined intelligence itself, and finally, how all of these ideas came together to give us a whole new way of looking at the world.
All right, let's go back to 1950. Our story starts with a question that sounds so simple, but at the time, science had absolutely no idea how to even begin answering it.
That's it. That one sentence from his paper, Computing Machinery and Intelligence, wasn't just some academic thought experiment. It was basically the starting gun for the entire field we now call artificial intelligence. But Turing knew right away. He had a problem.
See, this question didn't just come out of nowhere. It was built on decades of his own work, from his groundbreaking 1936 paper that first defined what computation even is, to his intense wartime experiences watching machines perform tasks that, for all intents and purposes, looked a lot like thinking.
He realized that asking, can machines think, was a bit like asking, what does a color blue sound like? The words themselves, machine and think, were just too vague, too loaded with centuries of philosophical baggage. To get a real scientific handle on it, he had to throw out the original question. And to do that, he first had to get crystal clear on what he meant by machine.
So, before he could even dream of tackling a word like thinking, Turing had to come up with a rock-solid, universal definition for what any machine could possibly do. He had to define the very act of computation itself. And what he came up with was this beautifully simple, abstract idea. Imagine an infinitely long strip of paper, like a tape, cut into squares. Then you have a little head that can do three things: read a symbol on a square, write a new one, and move one step to the left or right. That's all. It was basically modeled on the original computer, a person with a pencil and paper just following a list of instructions. Now, the crucial thing to get here is that the Turing machine is not a blueprint for a physical gadget. It's a thought experiment. It's an idea that captures the absolute core of any step-by-step process, any algorithm that anyone could ever come up with.
Okay, now here is where Turing makes this incredible leap. He realized you could design a special kind of Turing machine, a universal machine, and its only program would be this: read the instructions for any other Turing machine off the tape and then just do what it says. This one idea is the theoretical heart and soul of every single computer, smartphone, and server we use today. The idea that one machine can be programmed to become any other machine.
But here's the stunning paradox. By perfectly defining computation, Turing also discovered its hard limits. He proved that even for this all-powerful universal machine, there are some questions it can never, ever answer. The most famous example is the halting problem. You just can't write a single program that can look at any other program and tell you with 100% certainty if it will eventually stop or just get stuck running forever. And with that proof, he found a fundamental wall in the universe of logic. Some things are simply uncomputable.
So now that he had a really clear definition of a machine and knew its absolute limits, Turing could finally circle back to that other fuzzy, really difficult word, think.
He knew that trying to peek inside a machine's brain, or a person's for that matter, to see if it was really thinking was a total dead end. Right? We can't observe consciousness. So he came up with a test that cleverly sidesteps the entire problem by focusing only on what we can observe: behavior.
He proposed a game. A simple party game, really. You have an interrogator in one room. In another room, you have a man and a woman. The interrogator can only communicate with them through typewritten notes. The goal? The interrogator has to figure out which one is the woman. Now here's the twist. The woman tries to help the interrogator, but the man tries to trick them into thinking he's the woman.
And this is the genius move. Turing simply asks, what will happen when a machine takes the part of A in this game? So you take out the man, player A, who's trying to deceive, and you put a computer in his place. Now the interrogator's job is to figure out which one is the human and which one is the machine. The whole question changes. It's not can a machine think anymore. It's can a machine play this game so convincingly that an average person gets it wrong a significant amount of the time.
This completely reframes the entire problem. Suddenly, intelligence isn't some mysterious internal feeling. For the purpose of the game, intelligence becomes the performance of intelligence. It's an observable behavior you can actually measure based entirely on conversation.
And this is the profound question Turing just leaves hanging in the air for us. Think about it. We only assume other people are thinking based on how they act and what they say. So if a machine can perform so well that it's indistinguishable from a person, on what grounds do we deny it the label of thinking? It really forces you to check your own assumptions about what intelligence even is.
Now, this whole approach of breaking down huge, complex things into simple rules and observable behaviors, it went way beyond just computers. It gave Turing a brand new lens for looking at the natural world itself.
Later in his career, he got fascinated by how living things create patterns. He actually worked out the math to show how two simple chemicals, just reacting and spreading, could create the complex spots on a leopard or the stripes on a zebra. There's no grand designer or master blueprint telling them where to go. The complexity just emerges from simple, computable rules. And that idea, that mind-blowing complexity can grow without a designer, is a powerful echo of how we think about modern AI today, where intelligence might not be something we program, but something we grow.
And that brings us right up to the present day. His universal machine is the direct ancestor of all software. The imitation game, which we now call the Turing test, still shapes how we talk about AI's capabilities. And that beautiful idea of complex patterns emerging from simple rules, well, that's the fundamental principle behind the deep neural networks that are changing everything around us.
So if there's one thing to take away from all of this, it's this. Alan Turing's greatest gift wasn't a machine or even an answer. It was a powerful new toolkit for thinking. He gave us the concepts of computability, universality, and behavioral testing, a framework for rigorously investigating not just machines, but our own minds.
And that's where his work leaves us. By defining the machine so precisely, he forces us to turn around and look at ourselves. If our own intelligence is just the output of a biological machine that follows computable, though incredibly complex rules, then what are we? Are we ourselves just universal yet fundamentally limited computers? That's the question Turing left behind for us to wrestle with.